Okay, so the most recent Core 3 test you've done contained 3 topics: exponential functions, Simpson's rule, and volumes of evolution. The other 2 topics are dealt with on a separate video, and they're saved in the same playlist on our site. Now, I don't have the question sheet at home, so I've written it out again. It's pretty untidy, so apologies for that, but you should have your original test paper. Now, on this question, we've got some radioactive material. It's got Q units, and we've given how that radioactive material changes as a function of time as 10 e to the power of minus 1/10 of t. So that's the quantity after time t, where t equals starts at 0. So at the beginning we start with 10 units of this material, and we've got to calculate the rate of decrease in the amount of radioactivity when t equals 5, and it's worth 3 marks. Now, in Core 3 we're often given the amount and asked to work out the rate of change of the amount. In Core 4, when we come on to do differential equations, and we've actually already done that subject, and there's a video, as an example of a video in the playlist, we may have been given the rate of change of the substance and then asked to work backwards to how the quantity changes as a function of time. So once you crack these problems, then there's a different starting point, but a lot of the ideas in Core 3 questions like this and Core 4 questions like this are similar. So it's well worth working on in Core 3. So it will also help your Core 4. So let's get on with it then. So we know that Q, the quantity, equals 10 e to the minus 1/10 of t. Now, a simple sketch of that would mean it starts at 10 and it's an exponentially decaying function. It's going to look something like that. And the gradient tells us at any point on that curve tells us the rate of change of that quantity at an instant of time. So that's what it's asking us to do. It's to find the rate of change. So if we find the differential of Q, if we do dq by dt, we get a rate equation, and that's the rate of change of the quantity. So if we differentiate that with respect to time, we get minus e to the minus 1/10 of t. Now, if you found that difficult to differentiate, then come and see me or look at the chapters on differentiating exponential functions. You'll also need to differentiate other types of functions in Core 3 that you haven't done in Core 2. So that is how the quantity changes as a function of time, and this is basically the gradient at any point on that curve as a function of time, which is also the rate of change of the quantity. So now we substitute 5 into there. So if we substitute in now the value 5, we get e to the minus e to the minus 1/2, which we can substitute into our calculator carefully to get the quantity. Now, a mistake that we'll see a lot of students make here is that they put the time as 5 into this formula, which is the quantity. We wanted the rate of change of the quantity. So whenever you see rate of change, then you're looking for a differentiate with respect to time. And then we can work that out, and we get negative 0.6065. So so that's the increase effectively. So it's a negative increase. So the rate of decrease equals 0.607 to 3 significant figures. Okay, so that's part I, and as long as you remember to differentiate with respect to time, then you'll be okay, as long as obviously you can differentiate exponential functions. Now, the second part of the question, it went into great detail about what the half-life is. Now, they've explained what half-life is because not every student who does maths does physics, and so just to remind you, the half-life of a radioactive material is where the length of time it takes for the radioactive material to decay so that there's half of the original amount of radioactive material. So we start off with 10. So if I draw my curve again, now because it's 10, it's going to decay like that exponentially. It's going to asymptote to the x-axis to make sure it never crosses it. It starts at 10, so the half-life is going to be the time it takes to get to 5. And that time there is t, the half-life. Now they're not expecting you to draw a diagram necessarily like that in an exam, but it wouldn't do you any harm, because it certainly would help you to work out what's going on in the problem. So now we can work out the time when the quantity, sorry, that's q, not y, when the quantity q is half as much as when it started. So q equals 5. So what is the time when q equals 5? Now before I rush off to that, you might keep saying, well, why do you know it starts with 10? Well, if you think this axis starts when time, not x, sorry, when time equals 0. So if you substitute 0 into here, you get e to the 0, which is 1, so you're left with 10. So that's the starting point. And it's decaying because it's a negative coefficient with respect to time. If that was a positive, then it would start at 10 and exponentially increase rather than decay. Right, so we've got q equals 5, so we're going to work out 5 equals 10 e to the minus 1/10 of t, so we get a half equals e to the minus 1/10 of t. Now we've got to solve that equation now, and that takes us back to core 2, and if we take the natural logarithm of both sides, we get log of a half equals minus 1/10 of t log natural log of e, using the power law. Now, not many people actually write this step in. Most people, when they're doing these questions, go straight to this step. But that's why we can go straight to that step if you've forgotten. So that means that t is going to be minus 10 log of a half. Now you might worry that times are negative here. Whatever you do, don't try and correct it and think you're wrong. If you actually do log of a half, you'll find it's also a negative number. So we end up with a positive time. And if you stick that into your calculator, you get 6.93 to 3 significant figures. Now that's the exact answer, and that's an approximate answer. So that's our 4 marks for question 2. As long as you understand this concept that a half-life in this particular point is when the material that you start with, it starts at 10, decays to half its original amount, and that's the time it takes, then you'll be okay on that question. Now the final part asks us to think about, well, what happens after 2t, 3t, 4t, and there's a number of different ways you could go about it. If you weren't sure, well, you could always double that number, put it into this equation here, this formula here, and see what happens to q, and if you did, you'd find it actually comes to 2.5, and so on. So what you can say, there's a number of different ways, but one way of doing it would be just to sketch maybe, and say that if that's 10, and that's 5, sorry, that's 5, and that's t, then 2t, we're going to get 5 over 2, and then keep going on here, 3t, we're going to get 5 over 4, and so on. So it continues to halve, basically. Continues to halve. Apologies, you can see that, so I'll show you it again. It starts at 10, decaying away exponentially. You get 5, after 5 it's t, and then at 2t it'll be half of 5, 3t will be half of 5, so 5 over 4. So it's continuing to halve each time. So you could say that quantity q will continue to halve after each at each t, at each multiple of t, or something on those lines. Okay, so as long as you describe what's happening well enough, that's one way of doing it, then you will get the 2 marks at the end for that question.